Hi, everybody. My name is Hasti Vahidi, and I'm a PhD candidate in the Material Science and Engineering Department at UC Irvine. I am delighted to be here and talk to you about this project. As you can see, reversible enhancement of electronic conduction caused by phase transformation and interfacial segregation in an entropy-stabilized oxide. And this work has been recently published in Advanced Functional Materials Journal. And as you can see, there are a lot of funding agencies, a lot of people that have helped me in this work. And on the screen, you see this cartoon of our lab during COVID time. I'm thankful to my advisor and all my lab mates for their support. So let's get into high entropy or entropy stabilized oxides. So entropy stabilization is a material design strategy where you can design new materials, and in some way you can say that you're expanding the periodic table. If you think about it, if you have a binary ceramic oxide like cobalt oxide, you have cobalt cations and oxygen anions in your lattice. The difference between this binary oxide with the entropy stabilized oxide is that you're basically adding 4 more binary oxides into this material and use entropy to stabilize all these cations randomly in your single crystal structure, while you have oxygen anions or whatever anion that you have in your ceramic system reside in the anion lattice. So you'll end up with something like this schematic, and it will give you a lot of different opportunities, and you have the ability to tune your materials because of the compositional complexity and short-range disorder that comes with this new structure. For example, you have metal oxygen bond lengths and angles that can change because of the differences in the size and the electronic structure of these atoms, your cation coordination numbers, vibrational frequencies, oxidation states of this cation in your lattice, and so many more. And as a result of that, you have this phenomenal possibility to get novel functional properties. As an example, I want to point out this material. We studied a cobalt, copper, nickel, magnesium, and zinc oxide that I'm going to refer to as an ESO. Entropy-stabilized oxide has been studied as a conversion type electrode. In this graph, you're looking at specific capacity as a function of cycle number. And in a plot that is blue, you are seeing the basically capacity of this ESO material changing with cycle number, and you see a pretty stable trend. But when you look at other colors that are showing the other materials other than ESO, in this case, there are very similar materials with one less cation element than the ESO. So here we added 4, so we have total of 5 different cations sitting in the lattice, and that gives us certain amount of configurational entropy. But the other colors that are trends that are represented in other colors here don't have that, and so you can see that they don't have that capacity, and we think this better cycling stability is related to entropy stabilization. And so a lot of people are focusing on single phase materials in this field and these novel properties that I mentioned. This talk today is going to focus on multi-phase materials, and similar to many other fields where people basically create multifunctional, multi-phase materials or composites, our goal is to dive into multi-phase ESO materials and try to understand if they can be also a way to further increase the number of candidates that could be beneficial to a material science community. So we have a reversible second phase formation in these materials when we heat treat them. This XRD diagram is showing you the same sample mixture of all these oxides, the 5 different oxides that we described. If you mix them together and heat them in different temperatures for about 2 hours, you can see that depending on your temperature, your XRD data is changing and you have a different crystal structure. So you do have secondary phases at lower temperatures. As you go to around 1000 degrees C, you have a single phase crystal structure of this ESO that we're talking about. And then the interesting thing is that you can reverse this phase transformation by changing the heat treatment temperature again and go to lower temperature, heat treat, and get the secondary phases again. And now the question is, what can we do with this phase transformation and how can we basically control it? So this graph over here, work by some of our collaborators, is showing that the amount of secondary phase as a function of heat treatment time and get different amounts of this secondary phase. Also, as you can see in this plot, the grain size of these materials plays a role in the amount of secondary phase that you get, or the initiation temperature at which you are able to form these second phases. So we do think that that means that the grain boundaries that are different when you have different grain sizes, you have different volume fractions of grain boundaries. And as a result of that, we think that's why there's something going on with the grain boundary that is initiating this difference. So our goal here is to basically pose this question: can we tune electrical properties of this ESO by heat treatment and basically change our heat treatment and see how that microstructure evolves and how that functional property changes? We picked specifically 3 different spots on this graph. We have a single phase material, as-sintered ESO with no secondary phases. And we also picked a material that was heat treated for 2 hours and heat treated for 24 hours. We look at the evolution of electrical conductivity of these materials as a function of heat treatment hour. We have an ESO single or as-sintered sample, and we expect to be able to look at this structure, look at its morphology, and go ahead to our second sample that is a 2-hour heat treated at 700 degrees C. That's the temperature that we pick in this case. And then we go to our third sample that we call an ESO 24 that is actually heat treated in the same temperature, 700 degrees C for 24 hours. And our goal is to look at the structure and composition of second phases, grain interiors, and grain boundaries using transmission electron microscopy coupled with spectroscopy, STEM EDS and EELS. And also we do electrical conductivity measurements using EIS to look at charge transport in these materials and compare that as a function of this heat treatment or phase evolution. We're going to dive into the results. So first of all, we are looking at a single phase sample that we have. So here what I'm showing you is an XRD data that of this as-sintered single phase ESO sample, and you can see the rocksalt crystal structure and also an SEM image showing the morphology and the grains in this sample. And we focused on one of these grain boundaries in particular and look at the chemistry or composition of this using STEM EDS. As you can see in this map over here, we have segregation of copper to these grain boundaries in addition to segregation of some calcium and silicon inside of the grain boundaries that comes from more impurities in raw materials. In order to look at this a little more closely, we have the line profile across this arrow in this dark field image. And so here in this graph, you're looking at concentration in mole fraction as a function of distance. So as you can see, as we get close to the grain boundary, we have the segregation of copper. And then we have the segregation of calcium and silicon in the center, and then again, copper on the other side. So we have 2 layers of copper sitting by the grain boundary plane and also this amorphous phase at the grain boundary. However, this happens because copper wants to basically leave the crystal structure and it reduces first. It has a higher reducibility than other elements. We do believe this happens to reduce the energy, total energy of the system. Our grains, although I have to say they have a homogeneous composition all across, you can see that in these maps pretty clearly. And we collaborated with another group here at UC Irvine, where they helped us by density functional theory to look at the energy of grain boundary as a function of concentration of copper in grain boundaries. And so you can see that as you increase the amount of copper you have at the grain boundary, so number of atoms, as you can see, copper is shown in with the blue atom over here. So as you increase that, you're decreasing the energy, which is with agreement with our understanding of segregation, basically, to the grain boundary. So if we kind of sum up what we observed and understood from this spectroscopy data, we can look at this cartoon where we have the ESO rock salt grains and then copper at the grain boundaries. If we think about how conductivity can be changed in this material and what could be the role of all these morphological things that we saw, we can say that, okay, we see the copper at the grain boundary that can play a role in charge transport and also the grains. And we do know that there's a possibility of copper +1 existence in these materials that was previously shown. So we have the possibility of small polaron conductivity in this material. Additionally, we know from this DFT data that the changes in the first near neighbor charge density are the most around oxygen vacancies when you have copper atoms. So we think this is in agreement again with our observation of copper wanting to leave and join the grain boundaries. And we do think that that makes it highly likely for copper to actually reduce to copper +1 and potentially create copper +1, copper +2 pairs of small polarons. So moving to the multi-phase ESO samples, we see in the 2-hour sample, as you can see over here in this cartoon, we see the segregation of copper-rich particles to some of these grain boundaries, and all the other grains have homogeneous composition of all our cations and oxygen. If you look at the cartoon again, so pretty similar grains, we have some grain boundaries that have these new particles that are copper rich and some that are similar to the single phase grain boundaries. We think that upon heat treatment for 2 hours, some of the additional copper in the grains potentially left and started to form all these particles at the grain boundary. What happens is that we expect a slightly different conductivity from the grains because of the changes as copper left, and potentially it has created some copper vacancies. So when you look at the sample after 24 hours of heat treatment, you not only see that segregation of particles at the grain boundary, but the data that I'm showing here from this image coming from the inside of one of these grains shows that we have a segregation, basically the formation of copper-rich and cobalt-rich particles inside of the grains. And so now that we look at this cartoon, as I mentioned, that this schematic is showing you the grains. Again, we have the particles at the grain boundaries, and we have this formation of 2 new secondary phases inside of our grains. So our grain defect chemistry is further changed as copper and cobalt obviously have left the grain composition, the structure, to form these new phases. And so that could potentially impact the conductivity of this. So we do expect to see a change as we go from a single phase sample to a 2-hour and a 24-hour sample. Let's go and look at the conductivity data. First, I want to point out, just show you guys that I'm looking at the conductivity using electrochemical impedance spectroscopy. And first, we're looking at the single phase material to sort of understand that and get that out of the way. We're looking at this EIS spectrum, the Nyquist plot of the single phase data, and you are looking at this conductivity 1 semicircle that we have fed it with an RRQ equivalent circuit model at room temperature, and we repeat this in various different temperatures to calculate the activation energy. And the conductivity as a function of Evel's temperature is plotted over here. Activation energy is around 0.8 electron volts. And when we look at the data in the literature for all these binary oxides, that a lot of them are actually semiconductors, we do see that the conductivity of this ESO material that we measured in this first row colored in blue is actually similar to an average of all these other ones. So if you think about it, we have copper oxide, cobalt oxide, nickel oxide, that they are p-type semiconductors. We have zinc oxide that is an n-type semiconductor, and magnesium oxide that is a insulator. In some ways, we think that this demonstrates that the entropy in this case has not led to enhancement of electrical conductivity in the grains of the single phase sample. Even though we're looking at these binary oxides in comparison with our single phase, we have to keep that in mind that we are not directly changing the entropy. So maybe perhaps a more cohesive study for understanding the role of entropy would be to change the amount of entropy by adding different number of cations into its crystal structure and then looking at the impact of that in electrical conductivity. This is a demonstration of the new material that is created with all these cations as a function of what we had when we started, which are all those binary oxides. So it is not a direct comparison. Now let's look at the changes in conductivity as a function of heat treatment and this phase evolution that we discussed. So as you see in these cartoons, and also look at these Nyquist plots, we do have a very similar behavior for the 2-hour specimen, similar to the single phase. We have one semicircle that is fitted similarly, and its contribution from the grains. However, in the 24-hour sample, we believe that when all these grain boundaries are covered with these copper-rich particles, that's when you start to also see a contribution coming from this new grain boundary phase. And as a result of that, as you can see, we have two different semicircles showing up in our third specimen coming from the grain and grain boundaries respectively, and that has helped us to resolve the grain boundary conductivity in this material. So when you look at the conductivity plots, so you have log of conductivity as a function of inverse temperature, you see that your activation energy for the single phase is 0.8 electron volts, and then you go to lower values of 0.55 and 0.36 for the grain. Your grain boundary conductivity in the 24-hour specimen has a very similar activation energy. But if you look at the values of conductivity increases by about 2 orders of magnitude from the single phase sample to the 2-hour specimen inside of the grain, and then by 2 orders of magnitude from the grains to in the 24-hour sample compared to the 2-hour sample. So a total 4 order of magnitude increase in electrical conductivity here, which we believe is a copper +1, copper +2 small polaron hopping, or an N-type small polaron hopping in the grain. Additionally, the grain boundary conductivity is much lower than that of the grain, and we believe that actually is a copper 3+2+ small polaron hopping in a tenorite crystal structure, and that's different than that of the grains, which is actually what this ultimately leads to reduction in total conductivity. However, it's not that significant, and your total conductivity is also increasing. So essentially what we show here in this study is that when you have a multi-phase sample, you can use heat treatment, and you can use your grain boundaries as a reservoir or as an area where you can create these new phases, change the defect chemistry of your grain boundary, and then go ahead and tune your properties inside of the grain. We also show that conductivity in this material, similar to the phase transformation, it's actually reversible. So by applying voltage, we can see that we can go back and produce the same material like a single phase. So, and also with heat treatment. So in this graph over here, you're looking at this conductivity of this 24-hour specimen and the grain boundary conductivity over here. And what you can see is that as you basically go ahead and reset this with heat treatment, reset this material back to a single phase, and you measure its conductivity goes back to what that was initially for a single phase material demonstrated here. So this is a reversible property. In single phase materials, we have a very unstable crystal structure up to above 200 degrees C. It's pretty stable. After that, our material starts to phase transform when we were attempting to measure electrical conductivity. So that's something to keep in mind. And we also know that at least indirectly, entropy did not influence conductivity values and type. And in this case, we have electronic small polaron conductivity that is pretty much following the rule of mixture. With that, I want to thank you for listening. And I also want to thank everybody, including one of our main findings over here, the MERSEC. And thanks to my advisor for giving me the opportunity to do this work and also record this cool video.